Ladies and gentlemen, may I present you our second session chair, WPI Principal Investigator, Professor Miho Yamauchi of Kyushu University.
Thank you very much. I'm Miho Yamauchi from I²CNER in Kyushu University. It's my great pleasure to chair the next session, number 2. This session is related with 3 topics. One is hydrogen production, hydrogen storage materials, and fuel cells. The first speaker is Tatsumi Ishihara. He is principal investigator of I²CNER Kyushu University and professor Department Applied Chemistry Kyushu University. And, he get bachelor and master and PhD in Kyushu University, and he is given many awards. Especially, for example, Ichimura Research Award from New Technology Development Foundation in 2011. Today's his title is Hydrogen Production Based on Solar Water Splitting. Let's start.
Thank you very much for introductions. My name is Tatsumi Ishihara from the Hydrogen Production Divisions. And today's my talk is on the hydrogen production based on the solar water splittings. And this is the solar light, the distributions and also the efficiencies of the usage of the solar light. According to the Gibbs free energies, the required solar energies for the splitting of the hydrogen, splitting of the water into the hydrogen is 1,000 nanometers. So theoretically, we can achieve to the 75% of the efficiency for convert of the solar energy to the hydrogens. But of course, in the current systems, including the solar hydrogen electrolysis systems, such high efficiency cannot achieved. And this is because the generation of the electricity cannot effectively used for the production of hydrogens. And therefore, at the moment, the efficiency for solar energy into the hydrogen is still limited less than the 8%. Therefore, the objective of this group is to aim to produce hydrogen by using the solar energy with high rate and efficiencies. At the moment, there are 2 main systems is proposed for the production of hydrogen by using the solar energies. One is the so-called photocatalyst, and the other is a combination with solar cells with the electrolysis cells. And then in my groups, we are targeting to realize the improve of the efficiency of the 2 devices systems. And this so-called powder type photocatalyst is a simple but low efficiencies. But this combination of the electrolysis with solar cells is a little bit higher efficiency than that of the powder type photocatalyst, but the problem is the system is complicated and low-term stabilities. Therefore, both techniques are based on, in addition, both techniques are based on the single excitation and low efficiencies for production of hydrogens. Therefore, our group is mainly targeted on the double excitation system, so-called ZIT scheme, which is similar the excitation system of the current photosynthesis systems, and this is a keyword of these groups. And this is the structure of our groups and objectives. And our group is consist of 5 groups, and one is the most important groups is Professor Takahara's groups. This was studied on the interface structures, and as you may know, the interface structure is quite important for the separation of charge excited by the solar energies. And the Professor Adachi's groups is mainly study on the organic solar cells. And I and the Professor Sakai, which is new PI from this year, is on the development of the photocatalyst and the tandem type cells. And Professor Kiruna teams is study on the steam electrolyzer, which is highly efficient electrolysis, and therefore this steam electrolyzer can effectively convert the energy generated by solar to the hydrogens. Today in my talk, I mainly introduced this year's result in my groups. And my groups is study on the 2 types of the systems. One is powder types photocatalyst, but the modified with organic dyes. And then this system is also the double excitation systems. This means first excitation occurred in the inorganic materials, and then the electric charge is transferred to the organic dyes, and then excited again and passed to the co-catalyst of the platinums to generate hydrogens. And then if we connected this first excitation part to the second excitation part to the lead lines, then the system becomes the combination with the solar cells and also the generation of hydrogens. And this concept is a really interesting concept because in the daytime we generated electricity, and in the night the formed hydrogen is back to the electricities. Therefore, the one disadvantage of the solar cell can be solved by storing some part of the exciting solar energies to the hydrogen. Then we can recovery of the energies at the in the midnight by the formed hydrogens. And this year we applied to the narrowband semiconductor for the first excitation of the this double excitation system powder catalyst. And this is the hydrogen formation rate as a function of the wavelengths of the irradiated light. And in this catalyst, we use gallium nitride doped with zinc oxide as the first exciting inorganic semiconductors, and also the chromium tetraphenyl porphyrin, chrom TPP, is used for the organic dyes. And this is absorption spectrum of the chrom TPP, and this is the hydrogen generation rate without the chrom TPP, and this is the hydrogen generation modified with chrom TPP. As you can see here, the hydrogen formation rate becomes much improved by modified with chrom TPP. And this suggests that the chrom TPP is very effectively work as the separation of the irradiated separation of the exciting charge. And this is the magnified scheme figure of the hydrogen formation rate as a function of the visible light regions. And as you can see here, we observed hydrogen and oxygen by using the visible light, and at 440 nanometers visible light, we can achieve the quantum efficiency around 2%. And this value is one of the highest value reported in the open literatures. We also applied this double excitation system for using the electrolysis systems. And this is the scheme of the double electrode system using the calcium ferrite oxide and the tantalum oxide for each photofunctional electrode. And as you can see here, we observed very high open circuit potential, more than one volt. And this volt enough for the separation of the water into the hydrogen and oxygens. And then unfortunately, at the moment, the short circuit current is not high compared to the conventional solar cells, but we observed the formation of hydrogen and oxygens. Unfortunately, the amount of the oxygen is a little bit smaller than that of the waters, but anyway, we successfully demonstrated the formation of hydrogen, oxygen, and simultaneously with the electricities. And therefore, as I mentioned, that this concept is open the new schemes for the utilization of the solar energies. This means daytime electricity obtains, and night we can use the electricity. We can obtain the electricity by using the fuel cell with formed hydrogens. And this is a collaboration, SIPs, interdivisions, and also the outer research groups. And we have collaborated several number of the teams inside of our divisions, but we also have actively collaborated the outer side. Especially, we are now the strong relationship with Professor Rocket, who attended this conference also in the Illinois University to the analysis of the new materials. Then this is a proposed future work of our groups in order to improve the efficiencies we will apply for the further larger pi conjugated ring structure for the organic dyes, and also the preparation of planar type catalyst. This is more effective than the powder systems. This is because the no irradiations is expecting. And we also need to clarify the charge separation steps. In order to do this, we need to do the analysis of the interface structures. And then finally is the control of the interface. Okay, this is summary of my talk. This year we are very successfully demonstrated this gallium nitride as an initial excitation catalyst, and then we achieved reasonably high quantum energy efficiencies for the water splittings by using the visible light. And also the water splitting into the hydrogen oxygen with simultaneous generation of electricity was successfully demonstrated with combination of two inorganic semiconductors. And therefore, these results suggest that the double excitation system is not studied thoroughly up to now, but very effective for the charge separation and lead to the new field to use the solar energy to the formation of hydrogen and oxygens. Okay, thank you very much for your kind attention.